Hello everybody, this is Professor Algara in thermodynamics. Welcome to chapter number 7, which is named as entropy. So finally we reached this chapter. This is the last chapter in thermodynamics. As far as the content, I want to let you know that this is more like an informative chapter. I will not include this one on our final exam, and I just want you to get a little bit of information of what entropy is and how to deal with the entropy changes in a substance, and how to move forward so you can take this knowledge to thermodynamics too. Before I begin, let's just remember what we covered in chapter number 6. We were pretty much talking about the two statements of the second law, the Kelvin and the Clausius statement. We started doing exercises with cycles, different components connected all together. We had a homework, and it was a great chapter. So now this one is more, it has a lot of development on my side. We're going to pretty much explain how the entropy is increasing, the Clausius inequality, etc. So let's get started. So entropy. The second law of thermodynamics often leads to expressions that involve inequalities. An irreversible heat engine, for example, is less efficient than a reversible one operating between the same two thermal energy reservoirs. Just remember that when we talk about reversible system, we talk about the perfect system that has no that has nothing that will cause losses or things like that. And with that, I also want to remind you that irreversibilities are everything that will make your process not perfect, such as friction, gas expansions, and things like that. So we studied the efficiency of heat engines and heat pumps, refrigerators, and things like that by studying coefficients of performance and thermal efficiency as it is. So we're going to start by presenting the Clausius inequality. Okay, so pretty much let me just put this down. Okay, all right. So Clausius inequality. Clausius inequality is just a mathematical inequality, which is defined as the cyclic integral of dq over t, and this one has to be less or equals to 0. This is the Clausius inequality. Okay, this is just an inequality that expresses many things. From this one, we got the definition of entropy as a property, and pretty much that's how the whole entropy was discovered. Okay, this is our final point, and this is what we're getting to. So I'm gonna start demonstrating how this equation was developed. So at first, we only need to start by knowing the system that we're considering as it is, or how the system that we're studying is pretty much developed. So at first, we have something that is called a thermal reservoir, and everybody knows that, right? Okay, a thermal reservoir, and this thermal reservoir will have a temperature with it, and I'm gonna call that temperature TR. So TR, it's donated from the thermal reservoir, is giving a differential of QR. Okay, where is that Q going to? It's going to a system, and we know it's probably a small system, one component, another component, a third, and a fourth, and this system whole is just moving in a cycle, as we studied in the previous chapter. This whole thing is generating a work, and I'm gonna call a differential of a work of a reversible cycle. We're just considering that this is a reversible cycle or a cyclic device. Okay, reversible cyclic device. In previous chapters, pretty much we studied a thermal reservoir, and we had a thermal sink which is pretty much all the waste from this cycle that is given to the sink, and pretty much the two statements is like a work is being developed because a system is working between a thermal reservoir of a high temperature and low temperature, okay? Low temperature sink. But now it's gonna be different. This system is producing a differential of Q. But in the past, this Q was going to a sink, a low temperature sink. Now it's not going over there. It's going to a new system. And this new system, I'm gonna just call it as a system, okay, which is this one, by the dotted line. And dq is coming into this system, and because of dq, a new work it's been developed by this system, and I'm gonna call this a differential of work of the system. Perfect. And then something very important, we need to establish the boundaries of the system, and my boundaries are gonna be this whole thing, okay? And I'm gonna call this a combined system, okay? And that's my combined system because it will combine system right here, and it's going to combine the reversible system right there. This dq and the system, they have a temperature that varies with the time as this whole thing is expanding or contracting or being compressed, then it'll start just developing more temperature, less temperature. All right, so I want you to remember this because we're moving very quickly. What happened now? Now I'm going to do an energy balance of this system. And I just want to go back to this system. So if I take a look at the boundaries, which is this, and I do an energy balance, I need an energy balance which is, you know, the same thing we've been doing from chapter number 1, which is pretty much everything that comes in minus everything that comes out will be equal to the change of energy, right? So all the energy that comes in minus all the energy that comes out, it's equals to delta of the energy. We know that, that's pretty something that we remember. So let's just take a look. Cut. So this is something that we remember, energy that comes in minus energy that comes out, it's equals to the energy of the system. So this is pretty much a general equation that will work with all systems. So as you have to know whatever comes in or comes out as it crosses the boundaries, and remember this is the boundary. So what it's coming into my boundaries, so let me just do this. All right, so what is coming to my boundaries in will be this guy right here, the differential of QR. What is coming out of my system? This guy and this guy. So if I do energy balance in this whole equation, I'm gonna get the differential of QR, that's what's coming in, and now coming out will be the differential of the work of the reversible system plus the differential of the work of the system. And this whole thing, it's equals to, I'm gonna call it a differential of the energy of the combined system. If I want to rewrite this a little bit more, I can move into the next slide. And I'm gonna write the equation again, differential of QR minus the differential of the work of the reversible cycle plus the differential of the work of the system. It's equals to a differential of the energy of the combined system. And let's just rewrite this a little bit more. I'm gonna call this differential of work of the reversible plus the differential of the work of the system. I'm gonna recall it as differential of the work of the combined system. If I solve for differential of the work of the system, of the combined system, I'm gonna get that it's equals to dqr minus the differential of the energy of the combined system. And I'm going to call this one equation number 1. So far we're doing great. So before I move into the next equation, I just want you to remember from chapter 6 the following equation. QH over QL, it's equals to TH over TL. Okay, everybody remember that equation, and I hope you do. That's what I would ask if we were in the classroom. So the heat of the high temperature source over the heat of the low temperature source, it's equals to the relation between the temperatures related with each one of them. But now, how do I relate this whole thing with what I have? Let me just go back to the picture. Okay, so now my QH is actually QR, and my QL is actually Q by itself. TH is now giving us TR, and then TL is giving us T. Okay, so if I just use the equation from last chapter and I convert that into the new chapter, I will get something like this. Differential of QR over differential of Q, it's equals to TR over T. And these two equations are pretty similar. They connect in a similar way, and I'm just using the relationship based on the statements of the second law. Okay, using exactly the same thing. If you remember, just go to chapter number 6 and you will remember. I'm pretty sure of that. This is a little bit more developed in the book anyways. I'm gonna solve this equation, this one, a little bit more, and I'm gonna say that dqr over tr, it's equals to dq over t. And now what I want to do is solve for, I'm gonna solve that equation for dqr, and what I'm getting right now, it's equals to dqr, it's equals to tr, that multiplies dq over t. And this equation is going to be named 2. So what am I gonna do with all two equations? So I just want you to pay attention to these two equations. This is the first one, and this is the second one. Okay, take those equations into the next slide or your notes, because what I'm doing now, it's taking 2 into 1. And if I put everything together, it'll look to something like this. Differential of work of the combined system, it's equals to dr that multiplies dq over t minus the differential of the energy of the combined system. So what are the assumptions that I should make in order to develop this a little bit more? I'm just going to let the system go on a cycle to see how it will behave, and I'm gonna just integrate it as a cycle on both sides. And I'm gonna do the same thing with this, okay? So when you let the system go on a cycle, remember what will happen on a cycle. So you have 1 and 2. It goes from 1 to 2 and then from 2 to 1. What happened when you're working on a cycle? Do you remember? If you don't remember, E1, it's equals to E2. And therefore, delta E will be equals to 0. What I'm trying to say with this is that this component, when you let the system go on a cycle, will be equals to 0. And now if I rewrite the equation a little more, I'm gonna get work of the combined system, it's equals to dr. This one is constant because it comes from the reservoir that multiplies to the cyclic integral of dq over t. And this is quite important. So just take a look at this equation because now we're gonna work with this. Remember something, temperature is never negative because we're working in kelvins. Every time we're developing a thermodynamic equation, we work with Kelvin degrees, and there's no negative temperatures with kelvins. Why am I telling you this? It appears that the combined system is exchanging heat with a single thermal reservoir while involving work during this cycle. It's producing or consuming, we don't know that. Pretty much with the Kelvin statement of the second law, it states, or just remember what it states, and it states that no system can produce a net amount of work while operating in a cycle and exchanging heat with a single thermal energy reservoir. So if I take a look at this, which is the picture, the only way for the Kelvin statement to work, just remember we had a thermal energy reservoir, and the thermal energy reservoir was exchanging heat with a system, and this one was just given to a sink. You know, all the waste were going to a sink, to a thermal energy, and then this guy was producing work. What you have right here is not the same. Why is it not the same? Because now instead of going to a thermal sink, it's going to another system. Take a look at the picture. So if I really want to, if I want to follow what it's given by the Kelvin statement, work cannot be produced. So the only way, if we follow the Kelvin statement for this to produce work, is just the whole system is working between two thermal reservoirs, and that's not the case in this one. Therefore, the work is not being produced, the work it's being consumed. What I'm trying to tell you is that we can, by looking at the equation and using the Kelvin statement, we can know that this work has to be negative, or at least it has to be equal to zero. Okay, so the only way for me to find the behavior of this side of the equation, if I need to get negative, right, or zero, the temperature will never be negative. Okay, as I just said it, because we're working in Kelvin. So since this guy will always be positive, then the other component has to be either negative or zero. So in order for this equation to work, my cyclic integral of dq over t has to be less or equal to zero. And that's the Clausius inequality. And this inequality, it's valid for all thermodynamic cycles, reversibles or irreversibles, including the refrigeration cycles. So at the end of the equation, we just need to analyze this mathematically. And like I said, in order for the Kelvin statement to work, the work produced by the combined system has to be negative. The only way that this will be negative, it's going to be if TR it's either negative or dq over t it's negative. Since TR cannot be negative and it will be positive, the only thing that is left for this analysis is that the cyclic integral of dq over t will be less or equal to zero. And that's what we call the Clausius inequality. Okay? So what happened with this Clausius inequality? So he developed the inequality. He was just studying and he realized that this was a new equation. But he realized back in, I think it was 1865 or something like that, he realized that he had discovered a new thermodynamic property. And he chose to name this property as entropy. And he pretty much designed this entropy with the letter S. And that's how he defined entropy. Okay, so pretty much the equation will look something like this. So ds it's equals to dq over t. That's my equation for entropy. And let's just define the entropy as a definition. Entropy is an extensive property of a system, and sometimes it's referred as the total entropy. You can find things like entropy per unit mass, or you can find and then the equation will be like ds is equals to dq over t, and this is defined as entropy. Entropy is just another extensive property of a system, and sometimes it's referred as a total entropy. You can find something as entropy per unit mass, which is going to be a little s. It's the same way as you have heat and then heat and then heat, as the rate. So the unit for this property will be kilojoules per Kelvin, but then if you have per unit mass, it'll be kilojoules per kilograms Kelvin. So S is going to be equals, or the unit is going to be kilojoules per Kelvin. And then if it's per unit mass, the little s, it's kilojoules per kilograms Kelvin. All right. The entropy change of a system. So as you know, if we have a property, we study how this thing is changing within a system. So the entropy change of a system during a process can be pretty much determined by integrating this on both sides. And if I do that on both sides from 1 to 2, and then from 1 to 2, I'm gonna get that S2 minus S1, it's equals to the integral from 1 to 2 dq over t. Okay, and this is my equation for entropy. Again, this is kilojoules per Kelvin. So we have defined, the change of entropy instead of the entropy in itself. So entropy, it's just a property that will study the disorders of the molecules. So I just added a few videos on our Blackboard class. Please go and watch those videos in order to understand exactly how entropy will be in the world, how you can find entropy everywhere you go. It's not something easy to define, it's not something easy to understand, but you'll see with the exercise it gets a lot easier. So engineers are usually concerned with the changes in entropy. That's all what we study. Therefore, the entropy of a substance can be assigned zero value at some arbitrary selected reference state, as we do it with potential and kinetic energy. Usually we determine the entropy by using the equation that you can see right here, but also we can get those from the tables, and I'm going to get into that because I haven't defined this as it is. And now we're moving to the increase of entropy principle. This is something that pretty much we need to study, because I need to tell you that entropy is always increasing, but I want to develop why is that possible. So we're going to consider a cycle that is made up of two processes. We have process 1 and we have process 2. So the first process, we're going to say from 1 to 2, it's pretty much a process that could be either reversible or irreversible. We don't know. And remember, I just remember what I said on chapter number 6. A reversible process is not a perfect process. Reversible is a perfect process. And then from 2 to 1, I have something that is internal or internally reversible. Okay, so from 1 to 2, we have a process that we don't know that could be reversible or irreversible. And then from 2 to 1, we have a process that is internally reversible. So if I try to write an equation of those two processes in order to find my entropy, I would say that from 1 to 2, it could be dq over t. Yeah, you remember that? That was the equation we just developed. This one right here. Okay, but I'm just using integrals in this case. All right, this is from 1 to 2. Now, from 2 to 1, I have dq over t, which is internally reversible. The first one, I don't care, because this relation, which is the one that we just developed, it's for any cycle. It doesn't matter if it's reversible or irreversible. And this whole thing has to be less or equals to 0. Okay, we're just using the Clausius inequality in order to develop the whole thing. The second integral in the previous relation, or the relation that we just developed, is recognized as the entropy change. So I will have from 1 to 2 dq over t plus, and this is equals to 0. The only thing I did in this relation was to take this definition and put it as my entropy change. So if I keep moving with this, right, or if I rewrite this equation, I could say that S2 minus S1, it's more or equals to the integral of dq over t from 1 to 2. I just rearranged everything. Okay, S2 minus S1, it has to be more or equals to dq over t, the integral of that. If I keep rewriting this equation, I will get that ds it's equal or more than dq over t. So what happened with this, or the analysis that we're going to do with this, is what it's very important. So we have two cases. A case which is ds has to be more than dq over t, and ds has to be equals to dq over t. So the analysis that we can conclude of these actual relations is what is very important. So we have the first one here. ds is equals to dq over t, and if you realize this is for a reversible cycle, so pretty much something perfect, no problems, you're just consider a perfect system, and this is due purely by the heat exchange. All right, and then we have this one right here. This one, it's something that I don't know. How ds will be equals to dq over t? We know that dq over t, it's pretty much what is due to heat exchange. But I'm telling you that ds, the change in entropy, will be more than that. So if I'm telling you that ds will be more, the change of my entropy will be more than the entropy that is created due to the heat exchange, then it has to be something on this side that will make this one more than that. Because remember, this is the entropy of my system. And that's the analysis that we need to make. There has to be something that will be pretty much placed into this equation in order to work. So if I rewrite this equation, and I just want to, let me delete this equation for a little bit, and I'm just going to rewrite the equation as this. ds, it's equals to dq over t. Again, this is right here, it's due to the heat exchange. This has to be something else that we don't know, and we're gonna call this as generated, that we don't know, because that's what happened when pretty much Clausius was working with this new relation. He realized that the heat exchange was producing entropy, which is this, but he also realized that he still got a bigger value. But this value was not due to heat exchange, so something else was not included, and then he realized that this new entropy generated was caused by irreversibilities. So he realized that the entropy, the remaining of the value of the new property that he defined was created by irreversibilities. Remember, what are irreversibilities? What is the definition of those? It's pretty much something that is in your system that is causing your process to not be perfect. Okay, it's something that is preventing your process from perfection, and that will be friction, that will be gas expansions, that will be everything that we already talked in the previous chapters. So with that, we can pretty much say that this guy will be always positive or zero. And why is that? Because reversible process, they don't exist. The process irreversibles are the real process that we have in life. So it's either zero or positive. With that, I can conclude that the entropy generated could be more than zero, could be equal to zero, and could be less than zero. If it's more than zero, then we are in presence of a reversible process. If it's equal to zero, we have a reversible process. What happens when it's less than zero? Then this is an impossible process. So entropy, it's always generating. That's why this whole thing that we've been working, it's defined as the principle of the increase of entropy, or the entropy of increase principle. All right, so recapping a little bit more, we were studying the increase of the entropy principle. We had to process a process from 1 to 2, which was reversible or irreversible. Then we had from 2 to 1 a process that was internally reversible. When we pretty much wrote the equations down as of this process, which is the integral from 1 to 2 dq over t plus the integral from 2 to 1 dq over t for internally reversible. Then this is less or equals to 0. I just assumed that this guy, I didn't assume, I just put this guy as the entropy change. I rearrange everything into this equation. Then when we just study the equation in terms of differentials, seeing the two possible cases. So this case right here, it's the case for a perfect system and a reversible system, and the one on top is pretty much an irreversible system. When I study this one a little bit closely, then I will have this equation. ds is equals to dq over t. I know that dq over t, it's due to heat, and then I have another value that is generated and I don't know. Then this value was always positive. So pretty much when the tests were running 1, 2, 3, 4 times, Clausius realized that the entropy was always more than the one generated by the heat, and therefore he had another remaining of energy, and that remaining of energy he named it as the entropy generated. Okay, and that entropy generated was due to the irreversibilities that were taking place into the process. That's why that value always has to be positive or 0. When it's 0, we're in presence of a reversible process. When it's more than 0, the process will be irreversible or something real. And then when it's less than 0, then it's an impossible process. So all that definition, okay, will bring you into this. What is this? It's just a property, okay, and the value that we need to get, it's going to be get through different paths in order to tackle the exercises that we have with it. Entropy is a property, and thus the value of entropy of a system is fixed once the state of the system is fixed. Why am I telling you with this? Once you have two extensive properties, and you can define your state, and therefore you can find the values for entropy, just as you did with enthalpy or internal energy or the other properties that we study, specific volume, etc., etc., etc. How do we find those values is what really matters, okay? And you don't have to learn something new because it's gonna be the same way we've been finding the values in previous chapters. So when we're talking for pure substances like water or refrigerant 134A, we have to study the three different states. So this one, and that one. Compressed liquid, the mixture, and superheated vapor. Three of them, you're very familiar with this. So when you're studying the entropy change, which is S2 minus S1, you need to take a look at the properties that you have. If I have pressure and temperature, then I can define my state. If it's a compressed liquid, you might remember that you only have to approximate SF to your S1 at the temperature that you have. Once you move into the mixture, we have to play with equality. More likely you're gonna have temperature and quality. You could have temperature and pressure as well. And once you realize that you're in a mixture, then you need to use your equation in order to find your entropy. So if you might remember the equation, entropy at any point, it's equals to entropy of the fluid plus the quality that multiplies SFG. Okay, we've been working with that for a long time, and this shouldn't be a problem. Then, if you realize that you're in superheated vapor, you just need to go into those tables and find the superheated vapor. Moving along, I just want to define an isentropic process, so sorry for this, okay? But pretty much isentropic process, it's the process during which the entropy remains constant, okay? The entropy doesn't change, so S2, it's equals to S1. So, take a look at this. During an internally reversible adiabatic process, the entropy remains constant. Just remember the equation that we had. S2 minus S1 was equals to dq over T plus the entropy generated. This one was due to heat, and this one was due to irreversibilities in the process. So if they're telling you that it's internally reversible, that means that there's no entropy generated. This is equals to 0, and then they're telling you that it's adiabatic. If it's adiabatic, there's no heat exchange with the surroundings, and therefore this guy, it's also 0. So then you're gonna have S2 minus S1, it's equals to 0, therefore S2, it's equals to S1, and this is a what? Isentropic process. Super simple, and easy to make sense. So, I just want you to know that entropy is just another property. How we understand the entropy will change from person to person, but at the end, what the property studies itself, it's only the degree of disorder, how disorganized the molecules will be, or how the molecules are just flying around. How do you measure that? Okay, I have included more videos into the section of Blackboard, so please go and watch these videos because they're very important and informative. And I just want to tell you that this is the end as far as for the class goes. This chapter is not included on my final exam, and for this particular session we don't have homework related to this chapter. I just want you to go and read the chapter because I can tell you that you will be utilizing this chapter for thermodynamics too. I'm 100% sure of that, whether you are mechanical engineering degree or chemical engineering degree. You will have to play a little bit more with entropy. So guys, thank you very much for your time, and I hope everything makes sense a little bit. Remember that you have the resume content that I always have on my Blackboard. You also have a presentation and a bunch of different videos for you to understand this a little bit more. I just wanted to develop the equations myself with you so you can see exactly my point of view from the equations. But these equations are perfectly developed in the book, and if you read the book after my presentation, everything will make a little bit more sense. Thank you very much, and have a wonderful rest of your week. Thank you.